Hello, my name is Nancy Walker, and I am joined by my teammates, Alex, Michael, and Mark, to present our Drug Review Insights and Summarization tool. This project uses an AI-powered pipeline to analyze hundreds of thousands of patient drug reviews and transform that feedback into plain language summaries. Our goal is to help pharmacists and healthcare researchers quickly identify trends and insights from large volumes of patient experiences. I'll begin by reviewing the pre-processing steps for this project. We collected patient review data from the Kaggle and UCI repositories shown on this slide. After merging and cleaning the datasets, we were left with 219,206 patient reviews covering 4,211 unique drugs and 2,724 conditions. Each review included a 10-point rating, free text patient feedback, and helpfulness votes collected between 2008 and 2017. The pre-processing workflow consisted of several key steps. We first loaded and combined data from both sources into a unified format, then cleaned the data and created additional features to support analysis. Finally, we generated a data profile and saved the processed dataset for use in the AI-powered pipeline. The datasets were retrieved programmatically from the Kaggle and UCI repositories and loaded into Pandas for preprocessing. After ingestion, we validated the data by reviewing row counts, column structures, data types, and missing values. We identified a small amount of missing data in the conditions field, representing less than 1% of records, and filled these values with unknown, since condition was not a primary focus of our analysis. Once the data was validated, we moved on to creating a unified schema across both datasets. Although both datasets contain patient drug reviews, they use different column names and structures. To create a single analysis-ready dataset, we standardized the variables into a common schema. Shared fields such as drug name, condition, review text, and ratings were aligned across both sources, while source-specific variables were retained when available. As a result, the side effects and effectiveness fields contained missing or non-values for records originating from sources that did not collect this information. Because these were structurally missing values rather than data quality issues, they were left unchanged. Other cleaning steps included removing duplicate records, standardizing column names, converting dates into date-time format, and ensuring ratings were stored as numeric values. We also performed light text cleaning on patient reviews while preserving the original language. Since the generative AI model benefits from natural human-written text. To support analysis, we created several additional features, including review length, review year, and a helpfulness weighted rating. We also converted the 10-point rating scale into sediment categories, classifying ratings as negative, neutral, or positive. The final dataset contained the 219,206 patient reviews across 4,211 unique drugs and 2,724 conditions previously mentioned. Any remaining missing values were structurally expected and not indicative of data quality problems, resulting in a robust dataset for downstream analysis. After preprocessing, the clean datasets and summary profiles were saved for use in the AI-powered analysis pipeline. This completed the preprocessing phase of the project. I'll now hand it over to Alex, who will walk you through the API integration and prompt engineering portions of our workflow.
Hi everyone, thank you Nancy. I'm Alex and I led the API integration and prompt engineering for this project. I want to start by showing you exactly how generative AI fit into our pipeline, because I think we used an API can sound like a black box, so let me open it up. It worked in 3 steps. First, for every drug and condition we cared about, we built a structured data profile. That's the rating average, the median, the sentiment split between positive, neutral, and negative, plus a sample of real patient reviews pulled straight from the clean data set. So the model never worked from raw, messy text alone. It always had real numbers sitting next to real patient voices. Second, the profile got dropped into an engineered prompt, a raw prime system prompt, a defined output format, and a bit of few-shot guidance to keep the tone consistent. I'll go deeper on this in a minute. Third, that prompt went to Gemini 2.5 Flash, which returned a plain language clinical summary for that specific drug or condition. The end result was 11 outputs total, 1 overall dataset summary, 5 per drug summaries, and 5 per condition summaries. And critically, we cached every one of them into a file called AI summaries.json, which gets served directly into our Streamlit app, so end users get instant results, not a live API call every time. So why go to all this trouble? Because the scale of this dataset made traditional methods break down. We had 219,206 patient reviews across 4,211 drugs and 2,724 conditions, spanning 2008 to 2017. At that volume, manual review by a human analyst is just not feasible. Keyword and frequency counts, which is what a lot of traditional NLP gives you, miss nuance and clinical context. They can count how many times pain appears, but they can't tell you whether that pain got better or worse. And this audience we were building for was for pharmacists and healthcare researchers. This audience needs plain language that they can act on, not a data table they have to interpret themselves. On top of that, the dataset has no demographic context at all, so any deeper pattern is buried unless something can synthesizes into an actual narrative. And that's the gap. Therefore, we need an AI layer that could read, reason, and write, not just count. Prompt engineering is the part I want to spend the most time on because it's where the real learning happened and it's generally not as simple as it sounds. My first prompts were being close to summarize these drug reviews, and that output was generic. It basically just restated numbers I would already given it. 4 things changed that. First one being role priming. Role priming was the biggest unlock, telling the model you are a clinical data analyst, summarizing patient drug reviews for pharmacists, completely shifted the tone and depth. Suddenly, it was reasoning like an analyst instead of paraphrasing. Second, a structured output specification. I required 4 exact sections every time: patient experience overview, sentiment breakdown, key themes, and clinical relevance. That kept all 11 summaries consistent and machine parsable, which mattered when we assembled the final PDF report. Third, data injection, putting our actual computed statistics directly into the prompt text so the model was anchored to real numbers instead of hallucinating plausible sounding estimates. And fourth, a caching strategy, a use of use underscore cached underscore summaries flag that let the pipeline skip live API calls during development and just load the saved JSON. That saved real cost during iterative testing and made the live app instant for end users. So the question we were asked to reflect on directly, did generative AI actually improve our workflow as data scientists? My honest answer is yes, but with real caveats on both sides. On the delivery side, it replaced what would have been weeks of manual summarization with a single API call. It produced consistent, structured clinical narratives at scale across all 11 summaries. It surfaced themes, mood changes, bleeding patterns that the word count would never catch because that takes actual reading comprehension. And it enabled a non-technical audience to read these insights without needing a data science background, which was the entire point of the project. On the lesson side, prompt iteration was generally non-trivial. Vague prompts produced generic output, and getting it right took real, deliberate iteration, not luck. The model also reflects review bias. Volume doesn't equal clinical truth, since people with strong reactions are more likely to leave a review at all. The dataset's lack of demographic or comorbidity context limits how far you can push clinical inference from this alone. And practically, API costs require a caching strategy if you want to use this in production rather than just in a one-off notebook. So the takeaway I'm living with, generative AI is a real force multiplier for a data scientist, but only on top of solid analytical groundwork. It amplifies good data engineering, it doesn't replace it.
Thanks, Alex. I'm Michael. I'll be covering the exploratory data analysis. For this project, we analyzed over 219,000 patient reviews spanning 10 years, covering more than 4,200 drugs and 2,700 medical conditions. Each review contained a patient rating, written feedback, the drug and conditions being treated, and helpfulness votes from other patients. This provides both quantitative and qualitative insights into patient experiences. The goal of the exploratory analysis was to identify patterns in patient satisfactions, sentiment, and medication performances, and use those findings to support future AI generated summaries that can help users quickly understand large volumes of reviews. To better understand patient sentiment, we group reviews into three categories: positive, mixed, and negative. As shown here, about 66% of the reviews were positive, while roughly 25% were negative. Overall, the data suggests that most patients are satisfied with their medication. However, nearly 1 in 4 reviews reported negative experiences, often related to side effects, lack of effectiveness, and unmet expectations. This highlights the importance of looking beyond overall ratings and understand both positive and negative patient experience to gain a more complete picture of medication performance. So far, we looked at how patients rated their experience. The next question is what patients are actually saying in the review. One interesting finding is that happy and unhappy patients often use many of the same words. Terms like pain, anxiety, and weight appear frequently in both positive and negative reviews. The difference is the context. A positive review might say medication will relieve pain or reduce anxiety, while a negative review might describe the same issues as side effects caused by the drug. This highlights the limitation of looking at keywords alone. The same word can have very different meaning depending on how it's used. That's where AI becomes useful. Instead of simply counting words, AI can understand context and summarize what patients are actually saying at scale across thousands of reviews. Before comparing medication, I wanted to understand which conditions generate the most patient feedback. One result stood out immediately. Birth control accounts for about 17.5% of all reviews in the dataset, with nearly 38,000 reviews. That's more than 3 times the number of reviews for depression, which is the second most reviewed condition. This is important because it means the overall statistics can be heavily influenced by one category. If we look at the average ratings across the entire data set, we're really looking at a data set that is disproportionately shaped by contraceptive experiences. The key takeaway is that patient feedback should be analyzed within the context of the condition being treated rather relying solely on overall averages. We've seen that patient experience can vary significantly depending on the conditions being treated. The next step was to look at the individual medication and identify which drugs consistently receive the highest and lowest rating from patients. To make the comparison meaningful, I focus on medication with at least 200 reviews. This helps ensure the results are based on a substantial amount of patient feedback rather than a small sample size. On the positive side, Valtrex, Suboxone, Drysol all achieve average rating above 9 out of 10 with more than 90% sentiment. These medications appear to deliver consistently strong patient experiences. On the other end, drugs such as miconazole, suvorexant receive much lower rating and higher levels of negative sentiment, suggesting patients reported more challenges or dissatisfaction. One medication that stood out was phentermine, with over 730 reviews and an average rating of 8.8 out of 10. It combines both high patient satisfaction and a large volume of feedback, making it an excellent candidate for AI powered review summarization. To conclude the EDA portion of this presentation, most patients reported positive experiences with their medication, but satisfaction varies significantly across conditions and individual drugs. We found that negative reviews often contain some of the most detailed and actionable feedback, providing valuable insights into patient concerns and side effects. While these reviews should not be considered clinical evidence, they offer important real world perspective on patient experiences. At this point, I'll hand it over to Mark, who'll discuss the AI evaluation process.
Hi everyone, I'm Mark and I'll be covering the final two pieces of our project: how we evaluated the AI's output and the pipeline that ties everything together. So before I show you the results, let me walk you through how we actually graded the AI. We evaluated 10 entries total, 5 drugs and 5 conditions. For each one, we scored the AI across 3 categories. First one is sentiment tone accuracy. Did the AI correctly identify whether patients felt positive, negative, or mixed about a drug or condition? Key themes accuracy. Did the AI correctly identify the main topics patients were actually talking about? Things like side effects, effectiveness, or quality of life. And drug and condition comparison. Did the AI correctly identify which drugs perform better or worse relative to each other? The scoring scale was simple. A 3 means the AI's output was strong, supported by the actual data. A 2 means it was partially supported, and a 1 means it wasn't supported at all. So after the AI summaries were generated, my job was to actually evaluate whether the AI got it right. And honestly, the results were pretty strong. Sentiment tone was perfect across the board. The AI correctly characterized whether patients felt positive, negative, or mixed about every single drug and condition we looked at. Drug and condition comparisons scored 9 out of 10. The one weak spot was key themes, where only about 5 out of 10 hit a perfect score. And we'll get into why on the next slide. But the important thing here is that nothing scored a 1. The AI never completely missed. Now, the AI wasn't perfect, and I think it's important to be honest about that. The weakest area was key themes, and if you look at the table, you can see the yellow cells concentrated in that theme accuracy column. The reason this actually happened is pretty straightforward. We only fed the AI 3 sample reviews per drug and condition. So for something like birth control, which has over 38,000 reviews in the dataset, the AI was only seeing 3 of them. So that's a tiny window, and it shows. Beyond the accuracy issues, there are also some real-world considerations worth flagging. These are self-selected patient reviews, so people with extreme experiences are more likely to write them, which kind of skews the data. The summaries the AI generates should never be mistaken for clinical evidence. And in a production environment, sending patient-generated text to an external API would need to go through a HIPAA compliance review first. The bottom line is, the AI is a useful tool, but it needs a human in the loop before anything it generates get put in front of a clinical staff. So once the evaluation was done, all of that work, the AI summaries, the EDA charts, the accuracy evaluation, needed to go somewhere useful. That's where the PDF report comes in. It's the final deliverable that ties everything together into one document a pharmacist or healthcare researcher could actually pick up and read without needing a data science background. The report has 4 sections. It opens with an overall summary of the entire 219,000 review dataset. Then it goes into individual summaries for the 5 most reviewed drugs, followed by the 5 most reviewed conditions. And it closes with all 17 figures from the project, plus the AI accuracy evaluation we just walked through. The whole thing is generated programmatically using Python, so it's not a manually assembled document. It's an actual pipeline output. So everything we've seen so far, the pre-processing, the EDA, the API work, and the evaluation, all of that lives in 4 separate notebooks. My job for this phase was to write the script that ties all of it together into one pipeline that runs from start to finish with a single execution. It starts with a pre-flight check, validating that all the input files and notebooks are present before anything runs. Then it fires off pre-processing, which cleans and merges the raw data. From there, it runs EDA and visualizations, generating all 15 charts. Then it calls the Gemini API to produce the AI summaries. After that comes the PDF report and evaluation notebook. And finally, it runs a validation check at the end to confirm all 23 expected output files were actually produced. The whole pipeline runs in about 10 minutes, from raw data to final report. Now, a pipeline that just calls 4 notebooks in order sounds simple, but there were some real engineering challenges to solve. The first was orchestration. We used a library called Papermill to execute each notebook programmatically. So the whole thing runs automatically without anyone manually hitting run on each cell. The second challenge was compatibility. Each notebook was originally written to run on its own Colab environment. So the pipeline has to patch file paths and handle API key injections before each notebook fires. The third piece is the caching toggle. Every time we call the Gemini API, it costs time and money. Think of it like a taximeter running every time you test drive a car. So we built a switch that lets the pipeline skip the live API call entirely and just load the summaries we already generated and saved from a previous run. That way, during testing and development, we weren't paying for the same API call over and over again. And when we were ready for a fresh run, we could just flip the switch back. And finally, because the pipeline can fail silently, the last thing it does is check all 23 expected output files and confirm they're actually there before calling it done. So to wrap things up, I want to show you the live app we built to make all of this accessible. This is the Drug Review Insights and Summarization tool deployed on Streamlit. Here on the left side, you have the app's sidebar. It gives you a quick overview of what the tool does, the dataset it's working from, with over 200,000 reviews, over 4,000 drugs, and about 3,000 conditions spanning from 2008 to 2017. Shows you exactly which drugs and conditions are available in this demo and what's powering it under the hood, which is Gemini, Python, Pandas, Matplotlib, and Streamlit. Moving into the main area, the app is organized into 4 tabs. The first tab is a Drug and Condition Explorer, the main feature. You select any drug or condition from the dropdown, and it immediately pulls up all the key stats: total reviews, average rating, percentage of positive and negative reviews. Below that, you get the AI-generated summary from Gemini, written in plain language that a pharmacist or a healthcare professional could read it without any data background. And alongside it, you get the sentiment chart for context. Moving to the second tab, this is the overall dataset view. It gives you the big picture AI summary across all 219,000 reviews, along with the key EDA charts we saw earlier in the presentation. You can also see both evaluation figures right here on the bottom, so the accuracy detail results are built directly into the app. The third tab is where you can download the full PDF report, everything in one document, ready to share. And the last tab, it's the About page. It covers how the pipeline works, the dataset details, and the full team breakdown. The whole app is live and publicly accessible, and the link is in our GitHub repository. Again, this is Mark, and on behalf of my team, thank you for watching. You can find our full code on GitHub and try the live app yourself at the Streamlit link on the screen. We appreciate your time.